Hey guys, hi, welcome back. So in this video, we shall discuss about the thermodynamic pattern potential, the Maxwell equation. We will see the equilibrium conditions, and then we will see the trick related to the Maxwell equation, and we will solve a few problems. So let's see. The first topic is thermodynamic potential. Thermodynamic potential, it is representing the state of a system. What does thermodynamic system represent? Potential. Thermodynamic potential represents state of a system. That means using the thermodynamic potential, we can measure the energy of a system in terms of different variables. The energy of a system in terms of different variables, it can be measured using the thermodynamic potential. Suppose you know the pressure and temperature of a system, but you do not know what is the volume and entropy. Then using the thermodynamic potential, you can measure more state variables. Thermodynamic potential allows us to measure more state variables. This is an important thing. Now you see there are four thermodynamic potential or functions. The first is the Gibbs free energy. The second is Hallmans free energy. The third is internal energy. The fourth is enthalpy. Gibbs free energy is denoted by G. Hellman's free energy is denoted by A. Somewhere it will be denoted by F also. Here I have considered it to be A. Now internal energy is denoted by U. Enthalpy is denoted by H. These thermodynamic potential of functions, they are perfect differential. They are perfect differential. This is a very important point because this will be used in the Maxwell's equation also. What does perfect differential property mean? It means that the second partial differentiation relative to only second variable, the second partial differentiation relative to only second variable, it is not depending upon the order of the variable. Remember that the thermodynamic potential of function, they are perfect differential. That means the second partial differentiation relative to the only second variable, it is not depending on the order of the variable. Clear? So now let's see the Gibbs free energy. So it is given by G is equals to U plus PV minus TS. And taking the differentiation, you can write dG is equals to du plus this will give you PdV plus VdP minus TS on differentiation will give you minus TdS minus SDT. Now you see this du, it can be written as what? From the first law of thermodynamics, dq minus dw. So du is equals to, dq can be written as TdS, dw can be written as PdV. So you can write du is equals to TdS minus PdV. When you will substitute this value of du here, you can write dg is equals to TdS minus PdV plus the rest terms will be as it is. This TdS will cancel, this TdS, negative TdS, and PdV will cancel with PdV. And you can write dG is equals to what? VdP minus SDT. Now when you will write this particular equation in terms of chemical potential, then you can write dG is equals to VdP minus SDT plus mu dN. Mu is the chemical potential here. So from this equation, you can write volume V is equals to del G by del P, constant is T and N. The entropy S can be written as what? Del G by del T with a negative sign. The constant will be P and N. And this last term can be written as chemical potential is equals to del G by del N at constant pressure and temperature. So this is how you can write the volume, entropy, and chemical potential using the Gibbs free energy. All right. Now you see for spontaneous process, there will be some derivation and some assumption. From that, I'm not going into the detail. I'm just writing which is what is important for you. You remember that delta G, it is less than equals to 0 for a spontaneous process. All right. Now you see the condition for stable equilibrium for a system which has temperature and pressure constant. That means for a isothermal isobaric process, dG is equals to 0. If you see here, if you see this equation, G is a function of what? It is a function of the pressure and temperature. So when the pressure and temperature is 0, that means for a isothermal and isobaric process, dG is equals to 0. For equilibrium condition is what? dG is equals to 0. Yes or no? That means system at constant temperature and pressure, it is in stable equilibrium if the Gibbs function is having a minimum value. This is how you can calculate the equilibrium condition. All right, you have to remember what the Gibbs function is equals to. Next, you see the Hallmans free energy. It is denoted by A, and A is given by U minus Ts. So when you will take the differentiation, you can write dA is equals to du minus Tds minus SdT. So du can be written from the first law of thermodynamics, Tds minus Pdv, and dA will be equals to finally Tds and Tds will get cancelled, and dA is equals to minus Pdv minus SdT. Now again on introducing the chemical potential term, you will just write plus mu dN. Okay, so from here you can write the pressure P, it is equals to what? Minus del A del V at constant T and N. Entropy can be written as minus del A del T with constant V and N. And chemical potential can be written as del A del N at constant P and T. So this is how pressure, entropy and chemical potential can be written using the Hallmans free energy. Now you see here, this Hallmans free energy is a function of volume and temperature. So for a system whose volume and temperature is constant, that is for thermal isochronic process, the system will be in equilibrium when the Hallmans free function, it is having a minimum value, that is dA must be 0. This is the condition of equilibrium. You can calculate it from here. For constant volume and temperature, that is for isothermal and isochoric process, when the Helmholtz free function is of a minimum value, then it is in equilibrium, right? Next, you see enthalpy. So when a process takes place at constant pressure, the heat absorbed or released is equals to enthalpy change. Enthalpy change is what? When a process is taking place at constant pressure, then the heat absorbed or released, it is said to be enthalpy change. If you see this one, we will see in the later part. First, let's see what is enthalpy. Enthalpy is the sum of the internal energy and the product of pressure and volume. H is equals to U plus PV. Now, when you write its change, dH is equals to what? Taking differentiation, du plus PdV plus VdP. Again, if you write du from the first law of thermodynamics, TdS minus PdV, then you will get dH is equals to TdS plus VdP. Now you see, when you will take the pressure to be constant, then enthalpy change is equals to what? Heat absorbed or released. This is what it is said: when a process takes place at constant pressure, the heat absorbed or released, it is equals to what? Enthalpy change. Right, here you see, when you will introduce the chemical potential term, you can write dH is equals to what? TdS plus VdP plus mu dN. So from here you can write the temperature T is equals to del H by del S at constant TAN. Volume can be written as del H by del P at constant SNN, and chemical potential can be written as del H by del N at constant SNP. Now you see here, dH is a function of what? Entropy and pressure. So when the entropy is constant and the pressure is constant, then the system will be in what? Equilibrium. This is the equilibrium condition. dH will be equals to 0. All right. Now you see, again it is said here, at constant pressure dH is equals to TdS. That means in this case the enthalpy is representing the quantity of heat given to a system at constant pressure. All right. Next you see internal energy. Internal energy is denoted by U, and it can be given by the Gibbs equation only. du is equals to what? TdS minus PdV. So here you see, when you will introduce the chemical potential term, you can write du is equals to TdS minus PdV plus mu dN. Now you see, internal energy is a function of S and V. So again, when the entropy is constant and the volume is constant, then the system is in equilibrium. That is du is equals to 0. This is how you can get the equilibrium condition for all the four potentials. All right. Now we will see the Maxwell's equation. So for the first Maxwell equation, we will use the internal energy. For the second, we will use the Hallmans free energy. For the third, we will use enthalpy, and the fourth, you will use what? Gibbs free energy. So you have to remember from where you have to start, means which quantity will be used. So for Maxwell's equation, we will use the internal energy. We know an internal energy is written as du is equals to dq minus pdv. Right. Now you see, dq can be written as what? TdS. So du is equals to TdS minus PdV. So from here you can write the temperature is equals to del U del S at constant volume and del U del V at constant entropy. That is equals to minus P. Now you see, I have already said that the thermodynamic potentials of functions, they are partial differential. So we will use that property here, and you can write what? The differentiation of this one, that is del U del S at constant volume. First, this internal energy is differentiated at constant what? Volume. So del U del S at constant volume again it is differentiated with respect to volume at constant entropy. The reverse is done here. So you can see it is not depending upon the order. So you can write from this particular equation del u del s means what? It is T. So you can write del V del T, and outside the constant is S. It is equals to what? Del del S, del U del V means what? Minus P. So I've written here minus P at constant volume. This is how you can get the Maxwell equation. It's very easy. Just you have to write the internal energy equation, and already we have written now the temperature and volume, the quantities which we have evaluated already from that only. Okay. So this is the first Maxwell equation. Clear? Now let's see the Maxwell's second equation. So you will start from what? Hallmans free energy U is equal A is equals to U minus Ts. On taking a infinitesimal change in the process, dA can be written as what? Du minus SDT minus TdS. So du can be written as TdS minus PdV from the first law of thermodynamics. When you will substitute here, then you can write dA is equals to what? TdS and TdS will get cancelled. You can write minus PdV minus SDT. So from here you can write minus P is equals to del A del V at constant temperature, and minus S is equals to what? Del A del T at constant volume. Now again, using the property of the perfect differential, you can write what? Taking the differentiation del V of A at constant temperature, and then differentiating with respect to T at constant entropy, doing the reverse opposite in this side. So you can write from here that del T, this term is what? It is minus P, but both are negative, so it is getting cancelled. Okay, so you are having only P here, and it is equals to what? Del V of this term within the bracket is S at constant temperature. This is coming as it is. So this is the second Maxwell equation. These are very easy. You have to just remember, you have to start with what function you will use. In the first case, the internal energy. In the second, Hallmans free energy. In the third Maxwell equation, now what you will see? You will see that you will start with enthalpy. Enthalpy is H is equals to U plus PV. Again, taking the infinitesimal change in the process, DH is equals to what? DU plus PdV plus VdP from this equation. Again, if you substitute du from the first law of thermodynamics, TdS minus PdV. PdV and PdV will get cancelled, right? This will get cancelled. dH will be equals to TdS plus VdP. So from here, the temperature can be written as del S of H at constant pressure, and the volume can be written as what? Del P of H at constant entropy. So using the perfect differential property, here also you can do, you will get the same thing, del P of this one and S entropy. Means first taking the derivative with respect to what? S, then with respect to P. Clear? The same thing is done here. Now you see within the bracket del H del S is what? T, and here within the bracket del H del P is what? V. From here you can substitute. So this is the third one. I'm not going in too much detail because the same thing is repeated. You can just calculate the first one you see, and the next you can just remember the quantity which is used, the function which is used, and the process is quite same. All right. And the last one is the Maxwell's fourth equation. So here you will use the Gibbs free function. So G is equals to U plus PV minus TS. Taking the infinitesimal change in the process, you can write du plus PdV plus VdP minus SDT minus TdS. This will become PdV plus VdP. This will become SDT minus TdS. du is as it is. Again write du as what? TdS minus PdV from the first law. Cancelling TdS and PdV, you will have dG is equals to VdP minus SDT. So from here, volume and entropy we write. Here we are not using the chemical potential term, only we have the normal equation, and from there the quantities that you have already done what? For the potential that you have to find. And from there directly you have to use the property of perfect differential, and you can get the Maxwell's law. So this is the Maxwell's fourth law. Clear? So now let's see the trick. Okay. So for the first law, we will see for the first law first. So you can write TVPS in this way. So for the first law, you will put the arrow sign this way, downward. Same arrow side will be in this other side also. Now you remember that the arrow side is in below direction. Now, so in the below here the term is what? V. So that will be in the denominator. So you have to just write it as what? Del T del V. It is equals to what? Del P del S. All right. The constant for V is S here. For S it's V. Now you see S and P in the derivative, they are in the same side. So you have to put a negative sign. This is applicable in all the four equations. Clear? Now we will see the second one. For the second one, what you will do? For the third one, first you see the arrow is in this side. So the reverse of the arrow will be for the second one. So you have taken the reverse this side. in the below side also I've taken the reverse, and I will write it as what? It will be del P, del T, it is equals to del S, del V, right? Here V is constant, here T is constant. No S and P in the derivative in the same side, so there is no negative sign. Both are positive. Now we will see the third one. Third one arrow sign is in this direction. So you will write what? Del T, del P. Yes or no? It is equals to del S, del P. Clear? Here the constant is P, here the constant is T. Now S and P in the derivative in the right hand side it is together, so there will be a negative sign here. All right, so this is how you can do the Maxwell equation using the trick. You have to just remember that the arrow sign is in bottom for the first one, and for the third one it is in this direction. So arrow signs corresponding variable will be in the denominator. Clear? And S and P in the derivative, wherever it is together, that will be negative. So this is how you can remember. One suggestion from my side is that you need to practice the trick also 2 to 3 times, right? Because no trick can be remembered in just one look. So practice is 2 to 3 times. Now we will see a few problems related to whatever we have studied. So let's see the first question. What is it is said here? For a system with constant volume and temperature, the thermodynamic equilibrium corresponds to the stable with minimum. Here it is said for a system with constant volume and temperature. Volume and temperature is constant for a system, then the thermodynamic equilibrium, it will correspond to the stable with minimum what? When will be the thermodynamic equilibrium stable? For what quantity is having minimum value for this condition? That when the volume and temperature is constant for a system to be in stable thermal equilibrium, which out of this 4 quantities should have a minimum value? So we have already seen that for constant volume and temperature, we know that the Hallmans free energy A is equals to what? It is U minus Ts, right? When you will take the differentiation, dA is equals to du. Here you can write what? Minus Tds minus S dt. Du can be written from the first law of thermodynamics as what? Tds minus Pdv minus Tds minus S dt. So Tds and Tds will get cancelled. dA it is equals to what? Minus Pdv minus S dt. Now you see volume is constant, V, temperature is constant. Then dA is equals to what? 0. Yes or no? So for the Hallmans free energy, this particular condition is satisfied. That when the Hallmans free energy is having a minimum value, then the system is in stable thermal equilibrium at constant volume and temperature. All right. So the correct option is option A. Clear? So now let's see the next question. The Hallmans free energy of a photon gas, it is given by F is equals to minus A by 3 V T to the power 4. This is the Hallmans free energy of a photon gas. You have to calculate the entropy and pressure of the photon gas. So it's very simple. You have Hallmans free energy F is equals to minus A by 3 V 2 to the power 4. Right. We already know the Hallmans free energy, it is given by what? F is equals to U minus Ts. So when you will do the differentiation, you can write dF. Du can be written as what? Tds minus Pdv, and the Ts on differentiation can be written as T ds minus S dt. So this will get cancelled, and we can write dF it is equals to minus Pdv minus S dt. So from here we can write the entropy S, it is equals to what? Minus del F by what? Del T at constant volume, and the pressure can be written as minus del F by del V at constant T. So S is what? Entropy is just the differentiation of the Hallmans free energy with respect to T. So negative and negative will become positive. A by 3 V, it is constant. T to the power 4 on differentiation will give you what? 4 T to the power 3. So you can write S is equals to what? 4 by 3 A V T to the power 3. And similarly, P can be written as negative, negative is positive. A by 3 T to the power 4, it is constant. And del del V of V is what? 1. So this is the pressure. Clear? This is the entropy, this is the pressure of the photon gas. Now let's see the third question. The Gibbs free energy of a system G is equals to RT ln AP RT to the power 5 by 2, where A and R are constants. You have to find entropy. Gibbs free energy is given, you have to calculate entropy. See, we already know you can write the Gibbs free energy will give you the entropy to be minus del G del T at constant P. And if you don't remember, you can find out from the equation G is equals to U plus PV minus TS. From this also you can calculate. Just take the differentiation, then use the first law of thermodynamics, substitute the value of du, and from there you can get. Now when you will do the differentiation, S is equals to what? Negative sign I am keeping as it is, R is constant. So when you will differentiate this term, you will have what? Just T on differentiation, you will get what? Ln AP divided by what? RT whole to the power 5 by 2. Clear? Next you see plus sign, this time T is as it is ln of this one, that means 1 by ln. So RT whole to the power 5 by 2. And here you will have what? Here you will have AP. Again on differentiation you will have what? AP, right, divided by, here what you will have? R to the power, how much is there? R to the power 5 by 2. It is constant, it will be outside. On differentiation, what on differentiating what? 1 by t to the power 5 by 2, that means t to the power minus 5 by 2. What you will have here? You will have minus 5 by 2, and t to the power minus 5 by 2 minus 1. It will give you what? It will give you what? You can calculate and see, you will get t to the power minus 7 by 2. Alright. Then you see this bracket is as it is. Next you see it is equals to what? Minus r is constant. This is ln AP RT whole to the power how much? 5 by 2 plus. You see here, this r will cancel this r to the power 5 by 2, and this t to the power 5 by 2 plus t to the power 1. It will give you t to the power plus 7 by 2. So this t to the power plus 7 by 2 and this t to the power minus 7 by 2 will become what? It will be t to the power 0, that means 1. And AP will cancel AP. So here you will have only what? Minus 5 by 2. Clear? So S can be written as what? Minus a minus is plus. So 5 by 2 R minus ln, here one R is coming, R, and here you are having what? Ln AP by RT whole to the power 5 by 2. You can also write it as R, here you can write 5 by 2 minus ln AP divided by RT whole to the power 5 by 2. Alright, so this is what? This is the entropy of this particular system. Clear? So that's all in this video. Thank you so much. Have a good day.